This is the sixth lecture of the condensed matter course. In the last lecture, we discussed bonding, ionic bonding and covalent bonding. And there were three other types of bonding that were on a list that we were going to cover eventually: van der Waals bonding, metallic bonding, and hydrogen bonding. And for various reasons, I'm going to push those off until later. We'll try to pick them up where they fit in. Instead, what we're going to do is we're going to go back and reconsider the motion of atoms. We're going to simplify our life an awful lot today, and we're only going to consider the motion of atoms in one dimension. So for the purpose of today, we live in a one-dimensional world. We're going to summarize everything we know about bonding very simply. We're going to imagine we have two atoms some distance apart. Let's call the distance x. And there will be some potential v of x, which represents the force between the two atoms. And the potential v of x, as we discussed last time, it probably looks something like this. This is v of x. Something like that. So it has an attractive bonding force, and then if the atoms get too close, the potential shoots off to infinity. Okay. So what we're usually going to do is we're going to expand around the bottom of this minimum in a quadratic way and approximate it as a parabola. So we'll write v of x is some v naught. V naught is the bottom. V naught here, plus, let's call this distance here from here to here, let's call that x equilibrium. That's the bottom of the well. In other words, the distance at which the atoms would most like to sit, the minimum of the energy. So we'll go give a quadratic term here, x minus x equilibrium squared plus dot, dot, dot. Okay? So the energy is minimum if the two atoms are separated by this equilibrium distance, and then it's some sort of parabola if the atoms are either farther apart or closer together. Okay? Now, we should be a little bit cautious in doing this because occasionally, by approximating something as a parabola, you throw the baby out with the bathwater. And in particular, if you're worried about thermal expansion, it's very important to keep the dot, dot, dot terms. The fact that, in fact, the potential is not a parabola. So let's think about that for a second. How does thermal expansion happen? Well, if you're at low temperature, the atoms, you sort of think of like a particle in the bottom of a potential well, but what we're really talking about is the distance between the two atoms. But you can sort of think about that distance oscillating back and forth, just like it was a particle in the bottom of a well. So it oscillates back and forth. The atoms get farther apart and closer together. They oscillate back and forth. And pretty much the average distance stays at x equilibrium. But if we give the atoms some higher amount of energy here, or higher temperature, then the atoms can oscillate into here, but out all the way to here. Okay? Because the potential is steeper on the inside than it is on the outside. Generally, the atoms will be able to make it this x max here, and this x min will differ a different amount from x equilibrium. In particular, x max plus x min over 2 will be greater than x equilibrium at t equals 0. So the average distance that the atoms are from each other when they start oscillating will start to increase. And this comes from the fact that when the atoms oscillate, they can push in a little bit, but the potential is really steep, so they can't push in that much. But then when they oscillate out, the potential is softer, so they can go a much farther distance out. So this is what gives you thermal expansion, the particular form of the potential function that's softer as the atoms go away from each other and gets very, very steep when the atoms get close to each other. Okay? But as long as we're not considering things like thermal expansion, it's okay to just truncate our potential at quadratic order, and we have a pure Hooke's law type spring between our atoms. So far, so good? Everyone happy with that? Okay. So what we're going to do with the rest of the lecture is we're going to take a very simple model of atomic vibration, actually extremely simple model of atomic vibration, which is known as the monatomic harmonic chain. Harmonic chain, which is potentially the most important model we're going to study all year, not only because it happens to show up on the final exams very frequently. So monatomic means that there is only one type of atom. Harmonic means that it's going to be just simple springs between the atoms, and chains mean we're going to have a lot of these atoms. and the reason, and it's a very simple model, but the reason it's so important is because it introduces a lot of ideas that will come back over and over again throughout the term. So this is what it looks like. We have a bunch of atoms, and again, we're living in one dimension. They're lined up in a row. Each atom has some mass, m, all of them identical. And then there's a spring constant, all of the spring constants identical between the two atoms, kappa, kappa, kappa. And the kappa, the spring constant, comes from the expansion of the bonding potential, the harmonic expansion that we used up above. Okay? The equilibrium distance between the two atoms, x equilibrium, here, let's call it A for the purpose of argument. Generally, let me put it over here, this distance A is known as the lattice constant. And generally, we're going to use the word lattice constant frequently later in the term. Lattice constant generally means distance between identical atoms. And in this case, all of our atoms are identical, so it's just the distance between the atoms here. Let's define some positions here. So let's call this one x1. Maybe this one will be x2, x3, that. So we'll generally say that x sub n is position of atom n. And let's let xn superscript 0 be the equilibrium position of atom n. So that's, if you imagine letting the chain come to rest and you measure the positions, they're all spaced by a distance a. So xn0 is just, we can let it be, if we let the 0th atom start at position 0, then we can just set xn0 to be n times a, each atom separated by a distance a from the next. And the quantity we're actually interested in is the deviation from the equilibrium position, which we'll call delta x. So delta x sub n is x sub n minus xn naught. And what we're going to try to do is we're going to try to figure out the vibrations of this chain using completely classical physics to begin with, and we'll worry about quantum physics later. So you've probably done coupled spring and mass problems, probably in your first year, and it's pretty straightforward. What you're supposed to do is you're supposed to write down Newton's equations for all of the masses. So that's pretty easy. We just have F equals ma. So F on the atom n is mass times the acceleration, delta x double dot. And so what is the force on x on the nth mass? Well, okay, it has a force from the atom to its right. So it's kappa, Hooke's law, delta x n plus 1 minus delta x n. And then it has a force from the atom on its left, kappa delta x n minus 1 minus delta x n. I guess we can simplify that a little bit by writing it as kappa delta x n plus 1 plus delta x n minus 1 minus 2 delta x n. And what we'd like to solve for is we would like to solve for the normal modes, want normal modes of this chain. Normal mode, to remind you, means all atoms oscillate at a common frequency, And if you remember how you did this in your first year courses, it ended up being an eigenvalue problem with sort of a matrix, the dimension of the number of masses you have. Now, we might have an infinite number of masses here to deal with if we have a very long chain. So it looks like an infinitely large eigenvalue problem, and that might be sound a little bit frightening. But it turns out that solving problems like this is really easy, and we're going to use the same kind of trick over and over this year. And the trick is to guess the answer. And fortunately, the guesses are all the same, so it's easy to guess. The guess is you use what is known as a wave Ansatz. Ansatz is a German word that means something like guess. So we're going to guess that the solutions are waveforms. Someone who speaks German is probably saying, no, that's not what it means. Is that what you're saying? Yeah. I have no idea what it means. What does it mean? Does it mean rule of thumb or something? It means what? Okay. So I stand corrected. Thank you. Well, in physics, we use it to mean guess. So I don't know where it came from. All right. So the trick is we're going to guess that the form of the oscillations are simple waves. So we'll write down a waveform. Delta x is some constant a, e to the I omega t minus I k times x n naught. K here is the wave vector. And omega is the frequency. Now, this might be a little bit confusing because what we've written down is we've written down something complex, whereas we know the positions we're interested in are actually real. But this is just like when you study circuits in your first year. You're trying to think about currents that are oscillating, and instead of writing sines and cosines, you write down some sort of complex expression. And what you really mean is that you're supposed to take the real part at the end of the day. And that's what we really mean here, is at the end of the day you should take the real part. And the reason we do this is because it's always easier to work with exponentials than it is to work with sines and cosines. Now, because we're going to take the real part, we could put an overall minus sign up in the exponent and still get the same answer. So we can fix that omega is always greater than or equal to 0 without any loss of generality. Because if you just change the sign of everything in the exponent, once you take the real part, you end up getting the same result. But we must keep track of the fact that k can have either sign. K either sign, which corresponds to either a left-going wave or a right-going wave. The other thing, I guess, we should probably substitute in here the value of xn0, which is n times a. Okay? So then all we have to do is we have to take this wave ansatz, plug it into Newton's equations up there, and see what we get. All right? Well, if we plug it in on the left-hand side, we get minus m omega squared times a e to the I omega t minus I k n a. Right? Two derivatives brings down minus omega squared. And then on the right-hand side, we get kappa a. Let's see, yeah, okay. Kappa a, there's an e to the I omega t, which is common to all the terms. And then we get e to the minus I k n plus 1a plus e to the minus I k n minus 1a minus 2 e to the I k n a. Good? Now we can cancel out a whole bunch of things from this equation to simplify our life. So we get minus m omega squared equals kappa e to the I k a plus e to the minus I k a minus 2. Then we can use a trig identity that this thing is actually 2 times a cosine. And I'll actually move the m to the other side as well. And we get omega squared is kappa over m, 2 minus 2 cosine ka. Another trig identity that we can replace 1 minus cosine ka as sine squared of ka over 2. So that gives us a total of 4 total of 4 k over m times sine squared of ka over 2. And then I'll just take the square root of this whole equation. We get the final result. Omega is 2 square root of kappa over m, absolute value of sine ka over 2. And there we have it. We've solved for the frequency of the normal modes of our chain given the wave vector k. Now, it's probably worth plotting the answer. Here we go. So what does it look like? So here we have omega of k vertically. Then we have k horizontally. Okay, like this, and we'll put some points on. Let's make this point pi over a. maybe this point over here is minus pi over a. And we have this sine, absolute value of sine, kind of looks like this. Absolute value of sine kind of looks like this. That, okay, well, they're supposed to be the same height. And the height of this curve here is 2 square root of k over m, and it has its peak at pi over a and at minus pi over a. So this curve is known as a dispersion curve. Dispersion curve, which just means omega as a function of k. Now, somewhere in this picture, we should expect that there should be sound waves. We're talking about oscillations of some solid. I mean, we have our picture of a solid, which is just atoms stuck together with springs, and somewhere in there, there should be something that looks like sound waves. Where are the sound waves? Well, sound wave is a very long wavelength phenomenon. The definition of sound is that it should be a long wavelength oscillation. So we should really be looking down here at small k to look for sound waves. Just as a sort of mnemonic, that the sound that you hear has wavelength somewhere between like a centimeter and several meters. That's what you can hear depending on how good your ears are. Whereas the spacing between atoms that we're talking about, this pi over a here, the wavelength associated with this pi over a wave vector is on the order of the distance between atoms. Okay? A appears here, so 2 pi over the wave vector will give you a number on the order of the spacing between atoms. So most of this picture is very, very, very small wavelength compared to what we usually think of as sound. Sound is for very, very small wavelengths right down near the middle, near k equals 0. So let's actually try to figure out what the sound will be doing. The way we figure out what sound is doing is we go to k very close to 0. We expand this thing, we expand the sign, and we end up getting, what do we get? Well, the 1/2 cancels the 2, and we get square root of kappa over m times a times absolute k. And you'll remember the definition of the sound velocity is that frequency should be sound velocity times absolute k, and so we've derived sound velocity is square root of kappa over m times a. There we have our sound velocity. Now, if you took the fluids course last term, you'll remember that sound can also be defined in terms of things like compressibility of a fluid. And we should be able to get the same velocity of the sound from the formula that you derived last term, which is square root of 1 over density, mass density here, mass density, times the beta, the compressibility. Okay, so what's the mass density of our chain? That's easy. It's just 1 mass per distance a. And what's the compressibility? Well, first we have to figure out what the definition of compressibility is. It's minus 1 over v, d volume, d pressure, but we're in one dimension, so that gets replaced by minus 1 over length, d force. So if you think about one little piece of the chain, the length is 1 over a, length is a, and d force from Hooke's law is minus 1 over kappa. So the compressibility is just 1 over kappa a. And then if we plug in these two expressions into that, well, okay, let's do it here. This is then using this mass density and this compressibility. It's 1 over mass over a, and then 1 over kappa a. And that gives us, in fact, the same result that we had over here, square root of kappa over m times a. So it agrees with the expression we would get from a hydrodynamic picture of what sound waves should be. Okay? So everything, all sorts, seems to work pretty well. But that is way down here in this regime where the dispersion is linear. At higher k, it's not linear anymore. It starts to curve. Now think back to what it was that Debye was saying. Debye was saying he was going to just assume that the frequency of his sound modes was always linear in k. And then he cut off the spectrum at some maximum frequency. Well, it starts out linear. It doesn't stay linear. It curves. But indeed, it does have a maximum frequency above some frequency, there's no sound modes left. We found all of the normal modes of the system. This is all of them. And they have they only have frequencies between 0 and this frequency here. So Debye was right in that respect, that there really is a maximum sound wave frequency. It's not, well, we wouldn't call it sound, but it's a vibrational frequency of this chain. It's worth looking a little bit more closely at this point here, which is the highest frequency excitation, highest frequency normal mode. So that occurs at k equals pi over a. And how are we going to look at that more closely? Well, let's write down what the waveform would be. It's a e to the I omega t minus I pi over a times an, or it would be a e to the I omega t times minus 1 to the n, which means that every alternate even versus odd mass is moving in the opposite direction. And that's the highest frequency you can possibly get. OK, at this point, it's worth seeing a movie. So let me, here we go. See if it works today. Oh, beautiful. OK. So this is a program we can download from my website. It was written by Mike Glazer. It works on Windows. It works under Wine on Linux. I think it probably works on Mac, but I'm not sure about that. So the purpose of it is to show you what oscillations of one of these chains actually looks like in detail. So here we click monatomic chain, and we're going to click longitudinal, which means, oops, my gosh, change the speed. There we go. So you can change the speed of oscillation as well to make it easier to see. So what we have here in this corner, over here, you have this dispersion curve, and you can change k back and forth from high k to low k. So let's start with a fairly low k. Okay, make the speed fairly fast so you can see what's going on here. Okay, and you can see at fairly low k, come on. Yeah, you can see that this is sort of a long wavelength oscillation where everyone sloshes left, then sloshes to the right, and back and forth and back and forth. Now, as we increase k, it oscillates faster and faster, and the wavelength gets smaller and smaller, and until eventually it's oscillating really, really fast. And I'm going to have to slow down the speed so you can actually see what's going on. When you get to pi over a, this point here, you can see that every other mass is going in the opposite direction. And if you think about it for a while, you'll realize that there's a good reason why this is the highest frequency that you can possibly get, that you can't do any better than having every other mass opposing its neighbor. That if you want to get really high compression or high frequency, this is the highest frequency you could possibly get. OK, so I'll leave that for you guys to play with. I recommend messing around with it a little bit. We're going to have a problem turning that back on. All right, anyway. Good. So the most important thing that we deduced in this calculation is that the dispersion is periodic in k. It was proportional to a sine, and you'll see that the dispersion just keeps going exactly like itself over and over with sort of a periodicity. From here to here, you just keep replacing over and over. It looks exactly the same. This is not a coincidence. There's a general law that if you have something that's periodic in real space, like a chain, which has a periodicity delta x equals a, if you take a whole chain and you shift it over by a, you get back exactly the same chain again. If you have something that's periodic in real space, I should also say that real space is also known as direct space. That will imply that you have a dispersion which is periodic in k space, also known as reciprocal space. With a periodicity delta k equals 2 pi over a. And hence the name reciprocal, because here the a is upstairs and here the a is downstairs. Now the periodic, here's some more words that are going to be useful. The periodic unit here is known as the Brillouin zone. Maybe I'll write that definition a little bit because it's rather important. the periodic unit in K space, equals the Brouillon zone. And I apologize not only to German speakers but to French speakers now that, that this word Brouillon, Louis de Brouillon, is a word that English speakers have a terribly hard time pronouncing correctly, and probably anyone who speaks French will cringe at how I butcher it. But I'm not the only one. Every English speaker butchers this name. I really apologize about that. I almost failed French in high school, so I've never gotten any better at it. But I think it's something like Brouillon. That's my best guess about how it's supposed to be. Okay, now why is it, this is a very important principle that we have periodicity in K space. Why is it we have periodicity in K space? Well, let's find out. We have our waveform, delta xn, is a e to the I omega t minus I k n a. And then let's take k and shift it by 2 pi over a. Shift it by this entire length from here to here. We'll take some particular k and move it by 2 pi over a and see why we get back the same thing. Well, let's do that shift, e to the I omega t, and then we get minus I k plus 2 pi over a times na, and that equals a e to the I omega t minus I k n a times e to the minus I 2 pi n, and this thing here is 1. So in fact, we're getting back exactly the same waveform that we started with. The reason the dispersion curve looks the same at this point here and this point here is because they're describing exactly the same wave. The wave is unchanged by shifting k by 2 pi over a. Okay? This is an extremely important principle that will come back over and over and over. Now, this might be something that you'll find disturbing to begin with. Okay, now we have a problem here. Okay, now see if I can show you this. Oops, no, come back. Okay, let me show you something else. See if it comes back up eventually. Yes, okay, good. So you might ask, well, if k is the same as k plus 2 pi over a, what's the wavelength? Right? I mean, we usually think of the wavelength as being 2 pi over a. 2 pi over k equals the wavelength. 2 pi over k equals lambda. So if k is the same, if it's physically the same wave here and here, which one's the wavelength? Well, the way to understand that is from this picture here. So delta x, dx here, is plotted on the vertical axis, just to make it more clear. So I've plotted two waves here. One of them, the solid line, is at k, or actually the dashed line is k, and the solid line is at k plus 2 pi over a. Okay? The two curves agree at the position of the masses. And we're only talking about the displacement of the masses. The wave doesn't mean anything in between the position of the masses. The waveform is meant to describe what the masses are doing. You can't ask what is the value of the wave in between the masses. It doesn't have a value. The wave is meant to describe what the waves are doing, what the masses are doing. So it doesn't actually mean anything whether you extend the curve in the solid line way or the dashed line way in between the two masses. All that matters is what the masses, how much the individual masses are displaced. This is a phenomenon known as aliasing, and if you get this in your head, you'll understand pretty well why it is that this point and this point are actually describing the same wave, even though they have different k's. Okay? Good? All right. All right. So a little bit more nomenclature that's fairly useful. The real space lattice, let me define it as all points equivalent to x equals 0. So in our picture there, that would be xn equals n times a, because you can shift each point by an entire spring, and you get back to something that looks exactly the same. We also have the reciprocal space lattice, recip space lattice, which is all points in K space, equivalent to K equals 0. And for this particular model, it would then be, let's call those points G sub m equals 2 pi m over A. All those points are equivalent to K equals 0, shifted by 2 pi units of 2 pi over A. Now, it's actually something that is kind of interesting and will be important later on this year, is the e to the I gm xn is always equal to 1 for all of the points in the direct lattice and all the points in the reciprocal lattice. You can choose any combination of those points, and it will always give you 1. In fact, we're going to use that when we go to higher dimensions. We're going to use that property as a way to define the reciprocal lattice, so sort of put it in the back of your head. So one thing that's actually really useful for us to do at this point is to count the total number of waves that we've enumerated. We've solved for normal modes of the system, so how many of them are there? How many normal modes? Normal modes do we have? Well, we know that if we're counting different normal modes, we only have to look within the Brouillon zone. That if we go outside the Brouillon zone, we're describing something that's equivalent to another point inside the Brouillon zone. If we pick this point here, for example, it's equivalent to this point here. So we only have to describe things within the Brouillon zone. We have to figure out how many modes there are within the Brouillon zone. So we'll do the usual thing. Use periodic boundary conditions. Periodic boundaries. So we're putting the springs in a big circle. Let's let the circle have a length L, which is n. So n masses around in a circle, length L. So K then has to be 2 pi over L times some integer, P. P is an element of integers. Usual way that happens when we put everything in a periodic box. So the total number of modes is then the total range of Ks that we're looking at, 2 pi over A. So that's the entire range of Ks we're looking at, divided by the spacing between modes, 2 pi over L. So what we're doing is we're dividing up this Brouillon zone into lots of little pieces whose spacing is 2 pi over L. Okay? And so that is L over A, or n. So the total number of normal modes that we've solved for is n. There are n normal modes because there were n masses to begin with. This should not be surprising. You probably found this when you studied mass and spring problems before. If you start with n masses, you inevitably get n normal modes. And this is actually exactly what Debye had guessed before, that he wanted to have just the same number of modes as he had degrees of freedom in his system. Okay, so far, everything we've done is completely classical so far. So now we're going to move on to quantum mechanics. Quantum. So in quantum mechanics, there's a very simple rule, which is that if you have a normal mode, a classical normal mode of frequency omega, when you go to quantum mechanics, that becomes eigenstates with energy h bar E sub n equals h bar omega n plus 1/2. So what is this n telling us? This n is telling us you pick a particular normal mode that you're looking at, and this n is basically telling you the amplitude of that mode. That if you let it oscillate a lot, it has a lot of energy. If you let it oscillate a little bit, it has only a little bit of energy. So it's the difference between big N and small n. But the key thing is that the energy is quantized in integer units of this h bar omega. Now, this is an important definition that a quantum of vibration is a phonon, is known as a phonon, is a phonon. This is entirely analogous to a quantum of light being a photon, and its energy is h bar omega of k, depending on which k we're actually considering. So now I have to rant for a second about my normal pet peeve. So my rant is that if you open up a lot of books, they will tell you that a phonon is a quantum of vibrational energy, or a photon is a quantum of light energy. And I think that's actually a bad definition. I think you shouldn't specify energy, because it's true that a photon carries light, but it also carries angular momentum. It carries momentum. So why did you specify energy and not just specify that it's a quantum of light? Similarly with phonon here, a phonon carries energy, but it also carries momentum and other things. So I'm just going to say a quantum of vibration is the phonon. So to be a little bit more specific about what I mean here by a phonon, we pick a particular normal mode or a particular oscillation frequency, a particular wave vector k, and then we say if it's in its ground state, n equals 0, we say there are no phonons filling that state. If you excite n up to 1, we say there's one phonon in that mode. If we excite n up to 2, we say there's two phonons in that mode. It's exactly similar to what you do with photons and light. Now, of course, these phonons have to be bosons, because you can put phonon is a boson, because you can put more than one phonon in a given mode, given k mode. And its energy of the phonons in a particular k mode is h bar omega k. So this is the energy of the phonons in a particular k mode times the Bose factor. There's another indication that we're talking about bosons here. Bose factor plus 1/2. So the Bose factor here tells you the expected number of phonons in the particular mode at a given temperature. Okay? Is everyone comfortable with this? It should look a lot like what you did with photons earlier. Yes? Yeah, okay, good. So now what we can do is we can use this information to actually calculate the quantum mechanical heat capacity of our chain. Now, our chain is a rather simplified chain. It's a simplified model of what's going on. It has these a number of simplifications that the springs are only between nearest neighbors, and they're perfectly harmonic springs. But given those simplifications, what we're going to end up with is an exact answer for the heat capacity, no approximations at all. So the exact answer for the heat capacity, the total energy in the chain, is the sum over all of the modes, k equals minus pi over a to pi over a, of h bar omega, that mode, Bose factor, beta h bar omega k, plus 1/2, where the k's are taken in steps of 2 pi over L. Now, the usual way that we have before so many times is we can replace that sum with an integral dk over 2 pi times the length of the system, and we only have to integrate from minus pi over a to pi over a, because once we're outside the Bron zone, we're just redescribing some of the modes that we have already previously described. And if we count the total number of modes in the system, number of modes, it would be, we can write it as L over 2 pi, integral from minus pi over a to pi over a dk of the number 1. So we're just going to integrate over all the number of modes, count the total number of modes. That will give us, L over a, or the number of atoms in the system, which is, again, exactly similar to what Debye did. He cut off his integration over modes such that he would have exactly n modes in the system, no more, no less. So we use our omega of k that we derived, wherever it is. Off the top of the board, I'll write it again. We use 2 square root of kappa over m, absolute value sine of ka over 2. And if we plug that in to that sum, which we can turn into an integral, we will get the exact amount of energy in that system at any given temperature, and you can differentiate it to get the heat capacity. Debye used omega k equals v sound times absolute value of k. which agrees pretty well at small k, but doesn't agree at large k. But it was a pretty good approximation. Einstein, you can describe Einstein the same way. Einstein used all his oscillators, omega k, are at the same frequency, omega 0. That will give you the Einstein model, basically saying there's n oscillators and they all have the same frequency. At any rate, this enables us to write down, at least we can algebraically write it down, an exact expression for exactly the heat capacity of our chain quantum mechanically. There's one more rather important concept that we need to introduce today, which is, again, coming back to this idea that k and k plus are a member of the reciprocal lattice, 2 pi m over a, represent the same wave. I mean, the fact that we like to think of these phonons as being particles, the same way we think of photons as being, quantum mechanics is great because you can think of things as particles or waves and particles. You can go back and forth however you like. So sometimes we like to think about these phonons as being waves, and sometimes we like to think about them as being particles. And particles, we like to think about them as some object that's moving and it carries some amount of momentum. And in fact, sometimes in some models, these phonons can, more complicated models than this one, but phonons can scatter into things in their way. They can scatter into other phonons, scatter off of other phonons. They can scatter off of electrons. They can scatter off of light, for example. And we'll discuss some of those things later in the term. And the thing, you might think that there would be conserved momentum in the scattering process. But how is it possible we can conserve momentum in a scattering process if k isn't even well defined up to this change, that k and k plus g represent the same wave? So what one does is one define what is known as crystal momentum. Crystal wave. Well, okay, if it's k, it's the usual thing. If it's k, it's wave vector. If it's h bar k, it's momentum. Crystal momentum. So I'll put in the h bars. Crystal momentum, which is defined as h bar k modulo 2 pi over a. Now, what's modulo mean? Modulo is a word which means up to additive terms of. So, for example, 12 mod 5 equals 7 mod 5, modulo 5, because up to an additive term of 5, 12 and 7 are the same. 2 mod 5 is also the same. Okay? So, in other words, we're confessing that momentum is not conserved up to this factor of 2 pi over a, that you can take and give factors, additive terms of 2 pi over a freely. And this might disturb you because you might really like this thing called momentum conservation. But we really need to think back to why is it that we wanted momentum conservation in the first place. If you took the symmetry and relativity course last term, you'll remember that momentum conservation comes from a symmetry of space. And the symmetry of space that it came from was translational symmetry of space. And so you can translate your attention in space to anywhere you want, and all the laws of physics remain the same. In our model here, we don't have that anymore because we're only allowed to translate by A. Our translation group is smaller than out in the vacuum of space here. We're only allowed to translate by A, and because of that, we get a less strong conservation law, that instead of having momentum completely conserved, we only have momentum conserved up to 2 pi over a. Okay? So that's what's gone on here. It's very similar to this idea of Noether's theorem. It's not exactly Noether's theorem. Did people tell you about Emmy Noether? She was an amazing mathematician from the early part of the 1900s. Noether's theorem, strictly speaking, only applies to continuous symmetries, and this is a discrete symmetry, but it's very, very similar. And the reason we're getting less strong momentum conservation than we had when you think about regular particles in space is because we don't have the same translational symmetry of space. We only have a discrete translational symmetry. Okay, we have a few minutes left, so I'm going to add in a subject that I promised you I would address, and that subject is hydrogen bonding. So this is a totally different subject. I'm just picking this up because it's only going to take us 5 minutes. Hydrogen bonds. the general idea of a hydrogen bond is that hydrogen is a very special element because it's basically just a proton and an electron. So you might imagine having a big atom like, so here's a big atom like fluorine, and then it bonds to a hydrogen atom more or less ionically, but maybe slightly covalently. So the hydrogen atom is sitting out here. It's a proton, and its electron is more or less sitting over here. Its electron has been sucked to the fluorine atom, and what's been left behind is a bare proton. So this is our hydrogen nucleus, and what's left is a bare proton. Bare proton. And that's extremely special because it's the only time in chemistry where you ever get a bare proton that's not screened by some electrons around it. So whenever you have chemical bonding, usually some of the electrons are moved around, but there's always some shell left over, except in the case of hydrogen, where the one electron can be removed from it and you're left with a bare proton. And that's why hydrogen bonds in very special ways. So what can happen then is if you have another atom over here, say oxygen or maybe another fluorine atom, this bare proton will then make a very strong polarization of this fluorine atom and attract it. And this is the hydrogen bond, H bond, which is the bonding of the hydrogen to another atom via this strong dipole force. So let me show you a classic picture of this, how this shows up. So ice is sort of the classic example of that, where you have a hydrogen sitting on the surface of oxygen to make your H2O, but the oxygen has essentially removed the electrons from the hydrogen to a very large extent, leaving behind a bare bare nucleus, a bare proton. That bare proton polarizes this other electron over here and this other electron here on this oxygen and attracts the oxygen, making a very weak dotted bond to this big red oxygen sitting over here. And this, it's a weaker bond. It's a much weaker bond than a covalent bond or an ionic bond, but it's strong enough to freeze ice, below zero. So it's a strong enough bond to do some interesting things. Another classic case where hydrogen bonds enter is in biology, and particularly in DNA. If you took the biology segment last term, you'll recognize this as being DNA. If you didn't, now you're seeing it. This is DNA. And you'll see, so DNA is made up of this double strand, and right down the middle of the double strand, where the two strands zip together, there's a hydrogen bonded to an oxygen. This bond is the hydrogen bond. The hydrogen is really bonded to the nitrogen over here, and it has a weak bond to the oxygen over here. And you'll see that there's a similar hydrogen bond from a hydrogen here to a nitrogen here. Similarly, hydrogen bonds right down here, and hydrogen bonds down right here. So it's a hydrogen bond that holds together the DNA right down this zipping. So when you pull the strands of DNA apart, you're breaking hydrogen bonds. So I think that's all pretty much we need to know about hydrogen bonds, and I guess we will we'll pick up again tomorrow.